All right, welcome to Tolleson Physics. So what we're going to do is we're going to continue talking about simple harmonic motion today. Now what we're going to do is we're going to look at a spring that's attached to a mass that's going to vibrate back and forth. So easier to see than actually talk about. So here's a demonstration on the O-Physics website for a mass on a spring, and it's going to vibrate sideways. All right, so let's think about what's going on. We have this initial position. It's already stretched. So if you can see, it's at X max. So it's at its maximum stretch. So let's think about what does that mean for the forces and energy on this system? Well, the force, it's been displaced to the right on the picture. The force is trying to pull it back to the left, back to its equilibrium position that's denoted by X equals 0 on the slide. And so it's at its maximum stretch. It's trying to get pulled back to where it was. Let's think about that from an energy standpoint. Well, at this particular point, it's not moving, but it's stretched the spring. And so it has a maximum amount of elastic potential energy at this point. So now what's going to happen when we let the box go? So I'm going to hit run and notice it's going to move, slow down, turn around, move, slow down, turn around. And it's just going to go back and forth, back and forth. For an ideal motion, no friction, this will just keep going forever. And so it's going from its maximum to the right to its maximum to the left. That's the turnaround point for each case. But what's the kinetic energy in that case? Kinetic energy is 0, and the elastic potential energy is maximized at that point. Well, what's happening at the equilibrium position? Well, the equilibrium position in the middle, that is where there is no elastic potential energy. And since energy is conserved, that must be where the kinetic energy is. So if I click on Show Energy Graph, it's showing exactly where it is. And you can see at the turnaround points, the green line is kinetic energy and it's 0. And at the turnaround points, the spring potential energy is maximized. And at the middle, where X equals 0, well, that's where there's no stretch, so there's no elastic potential energy, and there's complete kinetic energy. So that's where it's going to be moving the fastest. All right, so I'm going to hit reset, and let's take a look at, let's graph this motion. And so I'm going to show these time graphs, and it's going to show a lot of stuff. There's a lot here. Position, velocity, acceleration, um, potential energy and kinetic energy. So let's hit run. And so it's starting at the maximum, right? You can see the maximum here. X is at the top, V is equals to 0. So let's hit run. And it moves to the left, then it moves to the right, then it moves to the left, and then it moves to the right, right? So the velocity keeps changing depending on what direction it's going in. Its distance is changing as well. So you can see that this, and we'll pause that, so you can see that this is a periodic motion. When we look at this position time graph, which is the orange line at the top, we're starting with maximum displacement. So this is a cosine curve, right? So we have a cosine curve for the orange line. How do you get velocity from a position time graph? Well, you look at the slope. So the slope starts at 0, so velocity is 0. The slope then becomes bigger negative until it crosses the 0 position line where it has the maximum negative slope. And then it's still going to the left, which is what negative means in this case, until it gets here, the turnaround point where the velocity equals 0. And then now we're moving in the positive direction. The slope becomes positive. And so that's how that continues. So what does this become? Well, this becomes a negative sine function. And for those of you in calculus, you can understand why that is. But you can get it simply from the slope of the position time graph. Same thing's true with acceleration. So when we look at the velocity time graph, the slope, which is negative to start with, gives us the acceleration. Here's the maximum velocity. It gives us 0 acceleration. Then it's a positive slope, so we get positive acceleration, so on, right? So it's all based on slope, all the basic kinematic principles that we had learned earlier this year. And then it also shows both the potential and kinetic energies, right? The kinetic energy, the green line at the bottom, Every time that velocity equals zero, kinetic energy equals zero. That's the way it should be, right? And so it doesn't matter whether it's positive or negative velocity, that's when we have our maximums. And then the potential energy mirrors that, right? At our maximum stretch, our maximum x, that's where you're going to have all your potential energy. When it's x equals zero, there's no potential energy. And so we can see those patterns going forward. So if we kind of summarize this, we look at forces. As the spring is pulled in one direction, the restoring force is pulling in the opposite direction. The force is proportional to the stretch, right? It's F equals negative kx. And so that is a proportional relationship. Now with energy, at the maximum stretch, all of the energy is stored as elastic potential energy. As we return to the equilibrium position where the elastic potential energy is zero, well then all the energy is kinetic. All right, so here's what the three graphs look like next to each other. So let's put equations to those. So the first equation, and this is actually on the AP equation sheet, is you have an amplitude. That's what A stands for. It's a cosine function. And then inside that cosine function, this is just related to how do you get time in seconds to mean something on the graph. And it's 2 pi times the frequency. Now, if you remember from before, 2 pi times the frequency is the same thing as angular displacement, and that's shorter to write, so I'm going to write it that way here. So x is a cosine function. So how do we get the velocity? Just as I had said before, slope of the line. It's a negative sine function. For those of you that know calculus, the omega pops out, and the velocity is a negative sine function. That's the main thing. And then the same thing with acceleration. You take the slope of the velocity time graph. Right? For those of you doing calculus, it's the derivative of velocity with respect to time. And so that gives us negative a cosine relationship. There's the omega 2 omega squared term that comes from doing the derivative. And so we're going to actually use these. But you don't need to know calculus to be able to understand that you're going from a cosine function with a position time graph to a negative sine function just based on slope alone. And then the acceleration is a negative cosine. All right, so now what I want you to do is I want you to consider a pendulum instead. We talked about springs. I want you to answer these three questions. So when a pendulum is pulled to its maximum height, what is the restoring force? And where's the energy stored? And then finally, what location will the pendulum travel the fastest and why? All right, so the restoring force is the gravitational force, Fg. Where is it stored? It's the gravitational potential energy due to the Earth's gravitational field. And where's the fastest it's going to travel? Well, at the bottom of the swing, where all of the energy from the gravitational potential energy has been transferred to kinetic energy. All right, so that was a closer look at how simple harmonic motion moves and some of the equations associated with its position, velocity, and acceleration. Next, we'll focus more on specifically springs and then pendulums.